Good afternoon, children. We are once again back with the same chapter, that is coordination chemistry or coordination compounds. If you remember, in the last class we had discussed about valence bond theory. In the last class we have discussed about valence bond theory. We have discussed the important postulates of valence bond theory. Okay, we have discussed the important postulates of valence bond theory. According to this theory, I had told you the different postulates and how this theory is applicable. In today's class, we are going to discuss the limitations of valence bond theory. We are going to discuss limitations of valence bond theory, or what are the limitations, what are the drawbacks of valence bond theory. See, the first limitation, if you want to write, please write it down. The first limitation of valence bond theory is that it involves a number of assumptions. When so many assumptions are there, that means we have to remember all those assumptions, as a result of which it becomes very difficult for us to remember all those assumptions. That is the first drawback. Second is that it does not give any quantitative interpretation of the magnetic data. It does not tell us anything about the magnetic data. In this theory, we are unable to find out what would be the magnetic nature of this compound. Third of all, it does not distinguish between weak and strong ligand. So we cannot distinguish a weak ligand from that of a strong ligand. And fourth of all, it does not explain the color exhibited by complexes. See, there are various complexes being formed. It does not tell us why should a complex have these different colors. So it does not tell us any it does not give us any information regarding the color of the complexes. Okay, then it does not give any exact explanation of the thermodynamic or the kinetic stability of the coordination compound. It does not give us an exact explanation of thermodynamic or the kinetic stabilities of the coordination compounds. Okay, it does not tell us about it. It does not make exact predictions regarding the tetrahedral and the square planar structure of the coordinated complexes. It does not make exact prediction regarding what the tetrahedral or the square planar structures of the four coordinated complexes will show. So ultimately, these are the certain limitations. The valence bond theory was able to explain many of the properties of coordination compound, but some of the properties it could not explain. That is, it involves a number of assumptions. It does not give quantitative interpretation of the magnetic data. It does not distinguish between the weak and the strong ligand. It does not explain the color exhibited by the complexes. It does not give an exact explanation of thermodynamic or the kinetic stabilities of the coordination compounds. It does not make exact prediction regarding the tetrahedral and the square planar structure of these four coordinated complex. Okay, all these things we can actually could not get this information of this valence bond theory. Okay, we could not get the information of this valence bond theory. So these are some of the predictions of this. These are some of the drawbacks of this valence bond theory. Okay, so have you understood drawbacks? I'm giving you 2 minutes time. Please copy down these drawbacks of the valence bond theory. Please copy it down, children. I'm giving you this 2 minutes time. By the meantime, you just copy down the drawbacks of this valence bond theory. Just copy it down. I hope we have copied down the limitations or the drawbacks or the shortcomings of this valence bond theory. Okay, I hope we have copied it. Yes, after that, the next topic we have is the crystal field theory. The next topic we have after valence bond theory. See, in valence bond theory, you have to study the important postulates of valence bond theory, how this valence bond theory is applicable in finding out the properties of coordination compound. After that, we have discussed the limitation of valence bond theory. Now we will discuss about the crystal field theory. Now we will discuss about the crystal field theory. According to the crystal field theory or CFT, the bonding between the central metal ion and the ligand is purely electrostatic. According to the crystal field theory, the bonding between the central metal ion and the ligand is purely electrostatic. Ligands are considered as point charges in case of anion or dipole in case of neutral molecules. Ligands are considered as point charges in case of anion or dipoles in case of neutral molecules. Okay, the 5d orbital in isolated gaseous metal atom or ion have the same energy. The 5d orbitals in isolated gaseous metal atom or ion have the same energy, that is, they are degenerate. However, in a complex, due to asymmetrical negative field or ligands, the d orbitals are no more degenerate and split into two sets of orbitals. They split into two sets of orbitals. The pattern of splitting depends upon the nature of the crystal field. The pattern of splitting depends upon the nature of the crystal field. The pattern of splitting depends upon the nature of the crystal field. How they will split, that will depend upon the nature of the crystal field. In octahedral environment, the dx square, dy square and dz square orbital are point towards the axis. They are pointed towards the axis. So, if I want to discuss with you the important points of crystal field theory, the first point is, according to crystal field theory, the bonding between central metal ion and ligand is purely electrostatic. Electrostatic means there is attraction between the positively charged central metal ion and the negatively charged ligands. Okay, so what is the type of attraction? The type of attraction is purely electrostatic. Ligands are considered as point charges in case of anion or dipoles in case of neutral molecules. So I can say that ligands are considered as point charges, okay, in case of anion, or they are considered as dipoles in case of neutral molecules. Okay, the 5d orbitals in isolated gaseous metal atom or ion have the same energy. The 5d orbitals, see, there are 5d orbitals and each of them are considered to be having the same energy. That is, we can say in the language of chemistry that they are degenerate orbitals. What is the meaning of degenerate? The meaning of degenerate actually means that they would be having the same energy. However, in a complex, due to asymmetrical negative field of ligands, in a complex due to asymmetrical negative field of ligands, the d orbitals are no more degenerate and split into two sets of orbitals. And the split in two sets of orbitals, the pattern of splitting depends upon the nature of the crystal field. The pattern of splitting depends upon the nature of the crystal field. The pattern of splitting depends upon the nature of the crystal field. The pattern of splitting depends upon the nature of the crystal field. Okay, that is, what is the nature of the crystal field? Depending upon it, the pattern actually changes. Okay, just copy down these 2 points. After that, we'll discuss the next points. Just copy down these 2 important points. After that, we'll discuss the next points. Okay, see, after that we are moving to the next point. According to the next point, what we have in an octahedral environment, the dx square, dy square and dz square orbitals which point towards the axis along the direction of ligand will experience more repulsion. So just remember, in octahedral complex, what is that? Octahedral complex has a square base and it has two pyramids, one upside and one is downside. So in that environment, if it involves dx square y square and dz square orbital, that is, it involves the eg orbital which point towards the axis along the direction of ligand will experience more repulsion and will be raised in energy. Okay, and it will be raised in energy, and the dxy, dyz and dzx orbitals which are directed between the axes will be lowered in energy as compared to the average energy in the in the spherical crystal field. Thus, in an octahedral complex, the degeneracy of the 5d orbital is partially removed due to the ligand electron metal electron repulsion to yield the 3 orbital of lower energy, one orbital of T2g set and 2 orbitals of Bg. So we are involving two sets of orbital, one from the T2g and both the orbital of the Eg orbital. Okay, so in this case we are actually arranging it. Next point is that the splitting of the degenerate orbital due to the presence of ligand, the splitting of the degenerate orbital, the splitting of the degenerate orbital due to the presence of ligand in a definite geometry is known as crystal field splitting, and the difference of energy between the two sets of degenerate orbital as a result of crystal field splitting is known as crystal field. It is called as crystal field stabilization energy. So I'm repeating it once again. The splitting of the degenerate orbital due to the presence of ligand is in a definite geometry is known as crystal field splitting, and the difference of energy between the two sets of degenerate orbital as a result of crystal field splitting is known as crystal field stabilization energy, or that is called CFAC, and it is usually denoted by the symbol del 0. So just remember, it is represented by the symbol del 0. So I'm giving you 2 minutes time, children. Please copy it. In the meantime, just copy it and check it. I will again discuss with you once again. Okay. I hope you have copied all these postulates. Okay, so if I summarize what we discussed in crystal field theory, according to this theory, the main postulates are that the bonding between the central metal ion and the ligands is simply electrostatic force of attraction between the positively charged central metal ion and the negatively charged or the neutral ligands. Next is among the five orbitals of the central metal ion, that is mostly a transition metal. What happens? All the orbitals have same energy. And what is that energy? As they are of same energy, so we can call these orbitals as degenerate orbitals. Okay. However, in a complex, due to the asymmetrical negative field of the ligand, the d orbitals are no more degenerate and splits into two sets of orbitals. The pattern of splitting depends upon the nature of the crystal field. Okay, pattern depends upon the nature of the crystal field. In an octahedral environment, the dx square, dy square, and dz square orbitals, which point towards the metal along the direction of the ligands, will experience more repulsion and will be raised in energy, and the dxy, dyz, and dxz orbitals, which are directed between the axes, will be lowered in energy as compared to the average energy in the spherical crystal field. Thus, in octahedral complex, the degeneracy of the 5d orbital is partially removed due to the ligand electron metal electron repulsion to yield three orbitals of lower energy, one orbital of the T2g and two orbitals of the higher energy, that is Eg. Okay. Now the next point is that the splitting of the degenerate orbitals due to the presence of ligand in a definite geometry is known as the crystal field splitting, and the difference of energy between the two sets of degenerate orbital as a result of crystal field splitting is known as crystal field stabilization energy. It is usually denoted by the symbol del zero. Okay. Now we are moving to the next postulates that will help you to understand how the crystal field theory actually works. Okay, children, just concentrate over here. See, there I have told you that the difference in energy between the two sets of degenerate orbital as a result of crystal field splitting is known as crystal field stabilization energy. It is known as crystal field stabilization energy, and it is usually denoted by the symbol del zero. The subscript 0 stands for octahedral. Okay, so O stands for the octahedral. It is found that Eg orbitals are 3 by 5 del 0 above the energy level, and T2g orbital 2 by 5, because see, it is exactly the opposite. Eg involves two orbitals, so the energy is 3 by 5, and T2g involves three orbitals, so the energy is 2 by 5 del 0 below the average energy level. Now here you can see one diagram. We have a metal M. This metal M now forms the central metal ion, right? This central metal ion is attached with 6 ligands because the complex is an octahedral. And regarding the energy difference, just note it down that we have the dx square, y square, dz square, dxy, dyz, and dzx. So this is the metal's d orbital. Average energy of d orbital is in the spherical crystal field theory. Now we have barycenter. Barycenter will tell you difference in energy in case of Eg. It is actually above the barycenter of 3 by 5, and the T2g is below the barycenter 2 by 5. So thus the splitting of d orbitals in a octahedral crystal field theory crystal field takes place. So in this way the energy difference takes place. I'm giving you 2 minutes time, children. Just copy down this diagram. Just copy down this diagram. Okay, I'm giving you just 2 minutes time, children. Just copy it down. I was children. What is actually happening? We have the metal M, right? In this metal M, it is attached as the central metal ion, right? And with the central metal ion, it is been attached, right? And here we have 6 ligands. How many ligands are there? The number of ligands present over here is 6, right? As it is octahedral crystal, so I can say the number of ligands are 6. Because of the octahedral nature, number of ligands present over here is 6, right? After that, what we have now, see in what is the energy difference. The energy difference that we have encountered is we have two sets of d orbitals, T2g and Eg. For the T2g we have dxy, dyz, dzx. For the Eg we have dx square, y square and dz square. Now when the metal is the average energy of the d orbital in the crystal field theory, and here it is the barycenter. In the barycenter, what we note down, that there is a great difference in the energy. That is, in case of Eg, the energy is 3 by 5 above the barycenter. In case of T2g, the energy is 2 by 5 above the barycenter. Now the next part of theory just tells you the magnitude of del 0 depends upon the field produced by the ligand and charge on the metal ion. The magnitude of this crystal field's stabilization energy depends upon the field produced by the ligand and charge on the metal ion. The arrangement of ligands in a series in order of the increasing field strength is called the spectrochemical series. So I can say over here that the actual series starts from here. That is I minus is less than Br, then thiocyanide, then Cl, then S minus 2, F minus, OH minus, then the oxalate, then the AQO, the NCS, EDTA minus 4, then amine, then ethylene diamine, then CN, then CO. This is actually order of the increasing field strength according to the spectrochemical series. According to the spectrochemical series, this is how the order of the energy takes place. Okay. Now, after that, in case of d square and d cube coordination entities, the d electron occupies the T2g orbital singly in accordance with Hund's rule for d4 ions. The electronic distribution depends on the crystal field stabilization energy. It depends on the crystal field stabilization energy, del 0, and the pairing energy P. The two options are as follows. Okay, that is, if del 0 is less than P, the fourth electron enters one of the Eg orbital, giving the configuration T3 2G E1G. Ligand for which del 0p are known as the weak field ligand from the high spin complex, and that forms the high spin complexes. Okay. Now, other one is in case of del 0p is greater than p, it becomes much more energetically favorable for the fourth electron to occupy T2g orbital with the configuration of T2g4 Eg0. Thus, the ligands for which del 0p are known as the strong field ligand and forms the low spin complexes. In tetrahedral coordination entities, the d orbital splitting is inverted and is smaller as compared to the octahedral field splitting. Okay, is smaller as compared to the octahedral splitting. Now I'm giving you just 2 minutes time. Just copy down the important points. After that, we'll proceed to the next part of the chapter. Please do it, children. I hope, children, you have copied these important points. Okay. Before we end today's class, I would like to summarize what we discussed. We had started the class with the limitations of valence bond theory. Now, what are limitations of valence bond theory? I had told you that it involves a number of assumptions. Unless and until we recollect those assumptions, we cannot discuss the theory. Next is it does not give a quantitative interpretation of the magnetic data. That is, we don't get a very clear idea of the magnetic data. It does not distinguish between a weak and a strong ligand. Okay. And next, it does not explain the color exhibited by complexes. That is, it does not tell us that why different ligands have different colors. Okay. And it does not give an exact explanation of the thermodynamic or the kinetic stabilities of the coordination compounds. Okay. thermodynamic or the kinetic stabilities of the coordination compound. And next important point is that it does not make the exact prediction regarding the tetrahedral and the square planar structure of the four coordinated complexes. Okay, it does not make any exact prediction regarding the tetrahedral and the square planar structure of the coordinated complex. All these are limitations of valence bond theory. As this valence bond theory was not been, now we have limitation, we actually developed the crystal field theory. And what are the major points of crystal field theory? The major important points of crystal field theory are that according to the crystal field theory, the bonding between the metal ion and the ligand is purely electrostatic. The 5d orbitals of the central metal ion, they have same energy and they are called as degenerate orbital. After that, in an octahedral environment, that dx square, dy square, and dz square, or that of the Eg orbitals which point towards the axis along the direction of the ligand, will experience more repulsion and will be raised in energy, and the dxy, dyz, and dzx orbitals which are directed toward the axis will be lowered in energy as compared to the average energy of the spherical crystal field. Thus, in octahedral complex, the degeneracy of the 5d orbitals is partially removed due to the ligand electron metal electron repulsion. Okay, these were the main important points. Then after that, I had told you that the magnitude of the crystal field theory depends on the field produced by the ligand and charge on the metal ion. The arrangement of ligand in a series in the order of increasing field strength is, I have told you, that is first of all iodide, then followed by Br minus, then thiocyanate, then Cl, then S minus 2, then F minus, then OH. This table is very important for exam point of view, so that you can understand the arrangement of ligands in the order of the increasing field strength. Okay, in D2 and D3 coordination entities, the d electron occupy the T2g orbital singly in accordance with Hund's rule. Okay, now here we have the two difference, that is the difference in the crystal field stabilization energy and P. What happens in that case, and what happens when the energy is less than P, when the energy is more than P. It becomes, if the energy is more than P, it becomes more energetically favorable for the fourth electron to occupy a T2g orbital. Okay. In tetrahedral coordination entities, the d orbital splitting is inverted and is smaller as compared to the octahedral field splitting. Okay. So these are the important points which we have discussed in our today's class. Go through these important points. I have given you time to copy down these points. Please copy them, study them thoroughly. If you have any problem regarding this important points, you have my WhatsApp number, you have my contact number, you can call me, or you can discuss them, or we can discuss them in your next class if you find these things are getting problematic. Okay, because see that the chapter is very scoring. In this chapter you have a huge opportunity to score, right? So please study the chapter thoroughly. Till then, children, goodbye.